All right, welcome to Data Within Reach and welcome to another 3-minute Rapid R tutorial. Today we're going to go over basic matrix algebra, which is really important for machine learning. And we're going to use vectors to do this. And I'd like to create a future video where I do matrix algebra using matrices. But we want to start with vectors because vectors are a fundamental data type in R, and they're more performant than doing work in matrices. In fact, if you want to really optimize something, you may find yourself taking a matrix and turning it into a collection of vectors. We'll explore the efficiency of using vectors in R by looking at the transpose operation, addition, subtraction, and scalar multiplication, and the scalar product. So let's get started. In R, vectors are a fundamental data structure. They allow for efficient calculation and form the basis for more complex operations. Let's take a quick look at how to create a vector. R's assignment operator is this little arrow sign, and to create a vector, you use that C. So this creates a vector V, and here we'll print out vector V and print what the vector value is. There you have it. Even though vectors are one-dimensional, they're like an n by 1 matrix, in certain operations, we need them to turn into matrices. So I'd like to show you how to do that in R by taking a vector and transposing it and then transposing it back again. Here we have the vector turned into a row matrix, and then the transpose of it using the T command. And let's, as before, print transposed vector as a column matrix, and there's the transposed vector. Vector addition and subtraction in R are highly optimized, and they're done on an element-wise basis. Here's an example. We've added a new vector, W, and we're going to create a third vector that is V plus W. Pretty straightforward, and print the results of that. And let's create an additional vector that is V minus W, and show the results for that. There you have it. Very fast, very efficient. Scalar multiplication works in R. So this is basically taking a constant and multiplying every element in the vector by a constant. So that's very straightforward and very efficient in R as well. Here's an example for scalar multiplication. We'll create a simple scalar, take our vector and multiply it by that scalar, and again, print the results. Exactly what you would expect. Now let's look at the scalar product, which is sometimes called the dot product. In R, when we're using vectors, we can compute this by taking the sum of the element-wise products. Multiply the elements, element by element, and then add them all together. And that gives you the dot product with respect to vectors. This is an important concept. In order to do it with a matrix, you actually have to transpose one of the matrices. So I want to put this here as a hook for our next video where we do all this with matrices. The scalar product actually multiplies across and down, and that's really important when it becomes two-dimensional matrices of any, or even three-dimensional matrices of any dimensionality greater than 1. You multiply across and down. In other words, you can multiply a 2 by 3 by a 3 by 2. We're going to explore this more when we talk about matrices in the next video, but I just wanted to put this here so folks would understand that things are a bit simplified when we use vectors in R. Using that transposed vector we created before, here's a more matrix math way of doing this calculation. Even though it purposefully does it a slower way, I'm doing it this way to illustrate the point. Vectors are fast and intuitive and an important part of linear algebra and furthermore, machine learning. Thanks for watching, and if you haven't already, please go ahead and subscribe. Once the next video is made, I'll put a link to it, and you could subscribe here as well. All right, well, thanks so much. Bye-bye. So with matrix algebra, two vectors are conformable for multiplication whenever the number of columns in the first vector is equal to the number of rows in the second vector.